Okay. Yihao, will you please start with your presentation about entitled how powerful are graph neural networks?
Okay, hello everyone. Today I'm going to present the paper, How Powerful Are Graph Neural Networks? It is published as the conference paper at ICLR 2019. And the authors are from MIT and Stanford University. And the two main authors are students, graduate students and PhD students respectively. And the last two authors are their supervisors respectively. One thing to notice is that Jure Lakozvek, he is a computer scientist and he is the chief scientist at Pinterest. So before we go into the paper directly, let me introduce some background knowledge about the graph and graph neural networks. So graph is a data structure comprising of nodes and edges connected together to represent information with no definite beginning or end. So you can see the graph that a graph is consisted of vertices and edges. And a typical graphical data in our daily life is like social network, where the nodes are people and the edges are the relationships between people. Okay, so let me put the definition of graph more formally. So we have a graph G, which is consisted of V and E. V stands for vertex and E stands for edges. And we also have, for each node, for each vertex, we have a node feature which describes the features of the node. And we can also possibly have edge features, which indicates the types of relationship between two nodes. And our goal to study the graph is to learn the node representations or graph representations, so that we can do some tasks like node classification or graph classification, etc.
Is there any examples for the edge features? For example, I understand, for example, in the social network, so there's a relation between friends, and there's a relation between maybe the enemies or family members or whatever it is. So
that's one example.
How does these edge features how does this edge features can be encoded? Is there an example or there's a follow examples later?
There no example in this slide, but edge features is also represented by like vector embeddings.
Yeah,
so
because in our work here, we will have given the method there's a caller relationship and a callee relationship.
Yeah.
Right. So we somehow may include these edge features later.
Yeah. So to understand graph neural network intuitively, first, because we want, our goal is to learn the node and graph representations, and we want this representation to incorporate the structural information of the graph. So one intuitive way is to aggregate the information for each node. We aggregate the information from its neighboring node, so that we can incorporate some structural information into this node. And for every node, we do the same work. So here, you can see the graph. The red triangle is the reference node. And each node here, we have a message. This message is the same. You can regard it as the node features. And when we aggregate the information from its neighboring, we just aggregate the message from its neighbor. Here is neighbor 1 and neighbor 2. and we transform the message to extract some features and sum the messages here to update the node feature of the reference node.
Here is fairly clear.
Yeah.
By the way, in your presentation, have you prepared a few questions for the students to answer?
No.
Oh, no worries. So let me think about the questions on the fly. Keep going on.
Okay. Okay. So so to put the definition more formally, we see the formula here. Here is an example of the graph, and if we want to aggregate the information from the neighboring nodes for this red node, then we use this formula to collect the information. Here, edge means the how do I put it? Maybe we see from the last part here, V is the neighboring node of the node U. So now we look at the node U, and V is the neighboring node of node U. And so here the set is the edge is the feature of the node. So here the set is the features of the neighboring node, and the feature of the node is the reference node itself. And we use the aggregate function to aggregate the information of this reference node and its neighboring node to update the node embedding. And the k-1 and k here is the case
layer.
Yeah.
The layer, right?
Yeah.
So this is more like a recursive definition. So if we want to know the nodes of k minus 1, we still need to aggregate its neighbors again.
Yeah.
Right.
Yeah.
So this aggregation function is a network, or it is be hard coded?
It's in the network.
So a network will learn a function to aggregate multiple aggregate all the messages sent from its neighbors.
Yeah, actually this aggregate function stands for a type of functions, and it can be many.
So it's a different type of edges will have different way of aggregation. Am I right, or is that your point? What's your point?
No. The point here is here the aggregate function is the abstract concept. It represents a set of functions. So we can to put it more concretely, we can look at some examples.
So do you have examples later?
Yes, I have.
Okay, sure.
Yeah. So after we aggregate the features for each node, then if we want to output the graph representations, then we just use a readout function to aggregate the node embedding of all the nodes. And this readout function can also be many types, and later I will explain. So next we look at two examples. So here the graph sage and the GCN graph convolutional network are two typical architectures of GNN. The graph sage here is using the max as the aggregation function to aggregate the information from the neighboring nodes. So here we can see that from the last layer's node embedding, we just put it into a linear layer, and then we use the max to aggregate the
this W is
a weight.
Is no, it's weight. It's a weight in the edge in the aggregation function,
right? Yes.
So this HU actually is a feature of its neighboring. The HU k-1 is the neighboring, the vectors of neighboring features
Yes.
And this W is learned during the training of the graph neural model.
Yes.
And then it's just choosing the max version. Okay.
Yeah. And the GCN network is using the mean to aggregate. So these two, the max and mean, are two types of aggregation functions. Yeah.
So here, a small question here. So in our problems, we have caller and I have callee, right?
Yeah.
So what if there's the multiple type of the ages? How could we aggregate the ages of different type?
Actually, one way is what I did. What I did to train.
Maybe we can design. I think we can discuss because this is more customized to our research problem. But I think there must be a way. In the extreme case, we can just design a gate. So in different or design an attention to aggregate the. We may use the mean to summarize the neighbors coming from the same type of age, and when they are summarized or aggregated, when the state of or when the ages of the same type has been aggregated, we can maybe train an attention model to verify which or assign a weight for which type is more important for us to synthesize the new uh, summary.
Yeah.
Okay, it's fairly clear until now. Please keep going on.
Okay. So as I just said, here the aggregate function is an abstract concept, and we can implement the aggregate function in many different ways, like the max function or the mean function or any function that can aggregate information. So here, let me also introduce the concept for the graph isomorphism problem. Here, the graph isomorphism problem asks whether two graphs are topologically identical. It means the structure of the graph are the same, whether the structure of the graph are the same. So the exact complexity class of the graph isomorphism problem is unknown. And that means it is not known to be solvable in polynomial time, or it is NP complete. But
sorry, so here I didn't get it. So what's the relation between what's the point that you mentioned the graph isomorphism problems?
Because the paper wants to study how powerful, how expressive is the graph neural networks. And that means because the graph neural networks want to learn the representation of the graph, right? And so one condition is that it wants to distinguish the two different structure of graph by two different representations. But if the graph neural network output the same representations with different graphs, then that means the
Do you consider it's not expressive enough?
Yeah, it's not powerful enough. So here we want to study the graph isomorphism problem to decide whether the two graphs are the same, have the same structure. And one way to decide that is using the Wechsler-Lehmann test. Here is this WL test is an efficient heuristic to solve the graph isomorphism problem. And you can see here in the graph, the first column is is an example of the graph structure, and initially we color all the nodes with blue color, and then for each node, for example, let me annotate. For node here, we aggregate the information from its neighboring node, and we can see that it's 3 blue node, and plus itself is a blue node. which is denoted here. So we denote it as a yellow. And then for this node, we can see that itself is a blue node. Its neighboring node has only 2 blue nodes. So we denote it as a green.
So what's the point of the colors?
Um,
So what's the basis or evidence, or based on what criteria should we attach or tint a new color on certain node?
the features. So initially it's the
It's pure blue.
yeah.
It's totally
So
blue.
that means the
Mm.
all the node features are the same.
Okay, so why we change it into green? So would you please re-emphasize it?
Because we want to represent the unique structure that this node have. For example, for this node, it has three neighbors, but for this node, it has only 2 neighbors. So we want to differentiate between these 2 nodes because they have different neighboring structure.
Mm-hmm.
So that we put them into different colors.
For now, we just based on the number of neighbors.
Yeah, and also their features.
The features are just blue. All the features are the same, right? For this example.
Yeah. Here in the first layer, all the features are the same, but in the second layer, then it becomes different because when we do the same process twice, then we can see when we are analyzing this node, then we can see that the initial color is yellow, and its neighboring node is one yellow and 2 green, right? So we can see that the structure becomes different and different, and by this way we iteratively do this process until reaching a stable coloring. This is the method of this WL test. So when we reaching a stable coloring, we compare the histogram of colors generated by the final graph, and we can see that these 2 histogram is the same, indicating that this 2 structure of the graph is the same. It's actually the same. This is the way the WL test. And we can observe that the way it tests the structure of the graph is very similar to how graph neural networks aggregate of information from neighboring nodes. So by this observation, the paper wants to study how expressive is the GNN. That means which graph can GNN distinguish, and what does GNN discriminate power depends on. So to study, you can look at this graph, for example. To study the representational power of a GNN, we want to analyze when a GNN maps to 2 nodes to the same location in the embedding space. Here, because we can see the graph structure here is obviously different, and then we want the GNN map to 2 different locations in the embedding space. And if the graph is exactly the same, have exactly the same structure, then we want the GNN map to the same location in the embedding. So the contribution of the paper has the following 4 points. Sorry. One is it showed that GNN are at most as powerful as the WL test to distinguish graph structures. And it has proved a theorem to establish conditions on the neighbor aggregation and graph readout function to so that the GNN is as powerful as the WL test. And it also identified the current variants of GNN, like the GCN and the graph SAGE that I just introduced. There are some graph structures that cannot be distinguished by those simple GNN structure. And at last, they also developed a simple neural architecture, GIN, and which has the equal power of WL test. So for the first point, they have shown the GNN are at most powerful as the WL test by proving the lemma here. The lemma says that for a graph G1 and G2, they are non-isomorphic. That means their structures are different. So if a graph neural network A maps G1 and G2 to different embeddings, then the WL test also decides that G1 and G2 are not isomorphic. So that means for any network, as long as the network can distinguish the graph, then the WL test can distinguish the graph.
So more like, but how about the vice? So if the WL graph isomorphism test it defines that G1 and G2 are isomorphic or not, whether the graph network can have different embeddings.
Yeah, that depends on the structure of the graph, the GNN. So
the structure of GNN means that how it aggregates.
Yes.
How it
the aggregation
readout and aggregation and readout.
Yeah.
So you will have more example of aggregation and readout, right?
Yeah.
Okay.
May I have a question?
Yeah.
So how to define the graph embedding of a graph? Because here, if you want to if you want to map G1 and G2 have a different embedding, you must have a graph embedding, not a node embedding.
Yeah.
But how to get the graph embedding?
So so here to have a graph level readout, we define a readout function.
So what's the readout function?
One example can be the sum of all the node embeddings.
Sum actually is no better than aggregation. So anyway, so somehow this aggregation and this readout are two abstract level of function, and different graph.
You can design different.
Define with it, but for example, if we write a code, there will always be an interface of readout.
Okay.
Okay, so this is the first point. So the expressive power of GNN cannot exceed the WL test. And the second point is that the paper has proved the theorem that under what condition the GNN has the same power as the WL test. So here is the two conditions. One is that f, the function f, and the function is defined.
Phi, right? It's called
phi. Okay. The function phi and function f. So the function f here is the aggregation function to aggregate the information of neighbors, and the phi here is to combine the information of all the neighbors and the self-nodes features. So both the f and phi should be injective. Injective means the function is 1 to 1. And for the readout function, it should be also injective. This theorem proves that.
So in that case, if the readout function is injective, it means the sum is not the function sum is not injective, right? Because it is a many to one. So you're saying that an injective function is a 1 to 1 function. one-to-one mapping relation.
Yeah.
Right. So I mean, I'm saying that as a sum, the function sum is not injective, because 1 and 1 can map to 2, and 0 and 2 can also map to 2, right?
Yeah.
Yeah. So I'm just saying that your example of sum is not injective, which means that if we're using sum as a readout function, the resulting gen is not so powerful as a WL test.
Yes. Yeah.
So you skip the proof, right?
Yeah, I skip.
Okay,
And
let's do the proof.
example not
Yeah.
included
Okay,
paper because
interested students can check the proof.
it's in the appendix. Yeah.
In paper. Yes.
And the third point is that by using this theorem 3.
By the way, so do you have an example? So at least for me, there's not such an intuitive about the expressiveness. Or maybe that's intuitive. If it is one-on-one, definitely there's no information loss, right? There's no information loss. But if it's one-to-many, that means information is aggregated too much. Then
Yeah.
the structure information is just lost.
Yeah, later I have the example.
Okay, great.
Yeah. So by using the aforementioned theorem, the paper developed.
By the way, but sometimes we have no choice but to using some way of aggregation. So in realistic GN model, it can hardly reach the effect of the WL test.
Yeah, and despite maybe some structures are less powerful, but it's good maybe enough. other properties, and
maybe it's good enough for
it's good enough. Yes.
Yeah.
So the paper, by using the theorem, the paper developed a simple architecture called the GIN, the graph isomorphism network that satisfy the conditions. So they have proved that by using MLP and this sum function here, it is satisfying the conditions in the aforementioned theorem. And generally, there may
is the sum function. You can see there's a sum function.
Yeah.
Or so the f they are using the sum, right? So if using sum, how does the sum function can keep the property of injection?
Hello, I think the injective definition is one direction, which means that one element in X corresponds to one element in Y, but not the reverse direction. So it still satisfies the injection property, right?
Okay, good explanation. So that makes sense.
Okay.
Yeah. So here, so Yihao, so you may need to verify. Sometimes I may made a mistake. You should correct me.
Okay. Okay. So thanks for the explanation. And here, generally, there may exist many other powerful GIN, and GIN is only the one. Is only one such examples. And here we can see some example aggregation function. So let's see the figure 2 here. You can see that the paper has ranked the expressive power for some min and max aggregators over a multiset. If you don't know what is multiset is it's the same as set, except that it can have
the elements may not be unique.
Same, right? Same element in the set.
Maybe you can raise an example to let students answer which example is a set, which example is a multi-set.
Okay. So maybe sorry. Yeah.
Okay, now it's time for question time. You can randomly pick a student in a group.
Okay. Maybe Yifan.
Okay. What's the problem?
Yeah, what's the problem? You
so
have,
here are
so you're
two.
not that focused. I find that when we have presentations, the students are not that focused. Okay, please go on. You can repeat the problem. You can repeat the question.
So suppose there are two sets here, and by definition, which one is set and which one is multiset?
Which one is set? Which one is multi-set?
Or you just need to answer which one is multiset.
Maybe the first one is multi-set. I don't know actually, because I just go to the toilet, so I didn't hear this part.
Okay. So the definition of multiset is that it's the same as set, except that multiset can have the same element.
Oh, okay.
So
the second is the multi-set. The first is the set. Okay.
Yeah, I think the definition of multiset is very popular in computer science. In the future, when we have the paper writing, and we may need to leverage the definition of multiset. So there already have a lot of mathematical tools for us to use. So when I was a PhD, when I was not that knowledgeable, I was reinventing a lot of concepts. So this finally I will find that this concept was already defined in some existing documents and literatures. So being knowledgeable is very useful for writing paper. Okay, keep going on.
Yeah. So here you can see that suppose this sixth node is the neighboring node, and we want to aggregate information from this six neighboring nodes, and the color representing red and blue color here, representing different node features. So the sum aggregator will be able to distinguish the structure. It will be able to incorporate the whole structure information, whereas the min and max aggregator can only cannot distinguish the structure here between the structure here and structure here.
Any example or any more illustration, and what information will the main function lost? So max is very obvious, right? Max is very obvious.
Yeah.
So
because
so let me let's raise an example. So why max? What information of max will the max function lose? So maybe I can raise against still Yufan. So think about Yufan. So can you answer these questions? Why max function is not so expressiveness, and what information will the max function lose?
I think the original is 4 blue and 2 red, and after the max, it only have 1 blue and 1 red, so it is lost.
Yihao, what's your point?
Actually, I think the graph here it wants to.
So let me explain here. So suppose giving a graph, there are 6 neighbors, right? Suppose there have suppose let's take either the simplest examples, and each node represents a scalar instead of vector. But in reality, it should be have high dimensional vector. But assuming that's a scalar, suppose it's 1, 2. Maybe the blue singular is 1, 1, 1, and the red one means 2, 2, right?
Yeah.
2, 2. So if we take a max, we can only take one node 2, right? And all the rest information are gone, right?
Yeah.
So suppose they have one blue and one red, we can get the value of 2, and there's one blue and 2 red, we'll still get the information of 2. So in this case, it's very hard for us to recover the network structure. So that's the point of the expressiveness, right?
Yes. Yes.
Can I ask one question? So when you take the max, do you take the maximum among the same set of elements, or you take the maximum globally?
Yeah. Maybe you just for one dimension, each dimension take a max.
I think Yufan and Ruofan's question are different, but those both are good questions. Yihao, can you answer that? I'm still curious about the answer.
The max here is element-wise.
Element-wise. So,
So what's the element? The definition of element is one of the embedding dimension or one of the embedding.
Is one of the embedding dimension.
Okay.
so it's more like the dimension-wise, right?
Yeah, yeah.
It's more like
Yeah,
dimension.
so the max, the output of this max
For
operation
example,
will
let
output
me
a
make an
vector.
example. Suppose this 1, 2, 3, and there's the 3, 2, 1, and after max it will become 33, right?
Yes, yes.
So that is about the max aggregation. So let me think about the injection property. So for injection property, giving the explanation of Ruofan, so each x can corresponding one y, right? But not necessarily is turned back. So sum actually can provide the property because x1, if we change it, if 1 to 1 plus 2, either change 1 or change 2, the y will change. But given y, assuming the y is sum is 3, we cannot uniquely identify an element in the space of X, right?
Yeah.
And you think about that. How about the max? And they also have the information loss, right? Well, let's keep going on. Let's keep going on. So I think the sum can still somehow lose the information. Still somehow lost the information. Change and change y. Oh yeah. So they're different. Okay, please go on. And how about the mean? How about the mean?
Mean, yeah, you can understand it in the same way, in a similar way, such that there is no difference. If we take the mean aggregator, there is no difference between this 3-node structure with this 6-node structure.
Okay, I got it.
And figure 3 is illustrating a similar concept, that when this is the examples that when the min max fail, the max fail and the max fail. Yeah. So here, maybe let me illustrate this example. Here, old node has the same feature embedding.
Yeah.
Yeah, and the mean will fill between these two structures, although these structures are the same, are different, but the mean will get the same result, and the same for max. Yeah.
Keep going on.
Okay. So just now we mentioned that the paper has developed the GIN structure, and it has conducted the experiments on the 9 graph classification benchmark. And the result shows that it performs quite well on the graph classification task, and it achieves the state of the art with the some MLP structure.
Okay, keep going on. So that's more just like a conclusion, right?
Yeah.
Okay, keep going on.
That's all. Yeah.
Okay, so very articulate. So I think Yihao articulates the paper presentations. I think all will be very clear. Is there any questions for this presentation? Okay, so if not, let's call it a day. And we should, if there's some students, maybe we can start another session, or if someone would like to join us, because this is not only for Yihao and Yihao's research work, but also somehow definitely related to Yufan's PhD work. If there are other students who would like to join and would find, I will create another session. Let's because we need to have a video. We will record the video later. So I will end these sessions and I will start one and share the links in the group. And you are free. You feel free. You feel free to join us. Okay. Thanks. Thanks Yihao, and thanks everyone for attending it. See you.
Okay, thank you.